Hello. Today I want to show off my mid-80s Microsoft training laboratory. This is actually made by Cleveland Institute of Electronics. This is created in the mid-80s, and this particular unit works with a 6809 8-bit processor. And this acrylic piece here, you can see different parts of the computer. Like here's the RAM, the ROM, a PIA, a keyboard controller, and then it's got a breadboard area where you can do experiments on it. And around the breadboard, you have the address, data, and control bus lines around it. And then on the right-hand side, you have the user interface. This is where you can enter, this is where you talk to the computer through the keypad, and you can look at its results through the display. I'm going to flip it on. You see it does this little song, and it displays a CIE bug, and then the rotating segments on the end here shows that it's running correctly as it should be. So everything's good. Now to access the CPU, you have to do it through the keyboard, and some of the things that you can do on the keyboard, you can, like it's got a button here, is accumulator A. You can actually look and see what's on the A accumulator on the processor itself. We press this and the A button, and it shows right now in accumulator A, it's got 00 is a data inside the accumulator A. And also you look at accumulator B, which is also 00. See, there's not a whole lot going on there now. And the CC red, which is the carry register, there's nothing on there. X register, nothing much on there. All right, pretty much all empty because there's no programs running on right now. But that's an easy way to access all the registers. When you're creating a program, then you want to test to find out what's going on with the processor. You can get feedback like that, see what's going on in the processor itself. Now to enter a program in here, you first have to put a RAM or an address we're going to write the program to, and the default is 0000, but I'm going to change this to 0100. So now I'm at address 0100, and it shows the data that currently is a 1 and a 3 at 0100. Now the reason I went to 0100 is because I want to kind of demonstrate a little bit how to enter this program here. So this is line 1. At 0100, you enter 8E, and then at 101, you enter a 20, and at 102, you enter a 00. And what this does, it loads register X with this value, with the 2000 hex. And the next line, at 103, you enter a 4F, which is a clear A. So I'm going to do a quick demonstration to kind of give you an idea of what it looks like to enter a program here. It's really not too hard, but it's kind of tedious and can be long. This is a really short, easy program just for comparing RAM. Now, right now it's set to change the address. You can tell it because you got the dots on the address. When you hit the address button here, it changes, put the dots on the data part. So now when you type something on here, it changes the data instead of changing the address. So at 0100, I'm going to put AE like it shows on there. And now see 100 now is AE. And I'm going to go up. Now 20 goes on to there. I'm going to add, then goes 00. And now I'm at 103. It shows there 103. And there I want 4F. And then the next address at 104, I want to put A7. And then at 105, I want 80. So this is basically how you go through and entering a program through assembly on this processor, on this laboratory. And there's some books out there, and it goes through and talks a lot about the different experiments that you can program through assembly, and also interface to different devices on this breadboard. Now the issue I have with this is that I type all this in, and I want to do it again later on. And when I turn this off, everything I typed in is gone because it doesn't save in it, right? Because it just wrote directly to RAM. When I wrote this in, I wrote directly to RAM. So I turn it off and turn it back on again, and then look back at address 0100, it's back to 13 again. It lost my program I typed in there, or lost the data I typed in there. So that was kind of a pain. So, and then I started thinking, well, I've got lots of ROM chips from when I used to own a computer company back in the late 90s. Although maybe I could find one that's electrically erasable that this board can handle. So, like here, I'll show you an example. So these are a bunch of EEPROMs that I've pulled from PCs from way back when. So most of them, the ones with the Windows, are out of luck because those are UV erasable. So I don't want a UV erasable one. I want something I can erase by using electric on it instead. So I looked around and I lucked out, and I found some 2864s, which is a EEPROM, electrically erasable, and it also, when you write to it with 5 volts, which is what's on the board already. So I don't have to worry about adding like a 12-volt language or voltage programming voltage to the board. Now to interface this, because I want to make it a little more permanent, right? So interface this, I don't want to just put it on here because there's not a whole lot of space on here. And if I put that chip on here, it's going to pretty much take up all the space. I won't be able to do my other experiments. So I looked around. At first, I was going to interface it by having a board just sit down with pins that stab down these here. These actually line up perfectly. So if you put a proto board across that and put pins on it, they will stab right down through there with no problem. But then it didn't seem all that great. And I also noticed it has an edge board connector back here. I just had to get an ohm meter and meter it out and figure out which one of these pins went to the address and data and the control bus, and found they pretty much all go there. So I said, well, I'll just use that. So I went through on my old junk drawers, and I found an edge connector that would fit on there. And then I have a large spool of 50-pin ribbon cable, and I have some ends I can put on it. And so to make this work, I had to actually put 2 ends to get the data off that edge connector because they're too far apart to go to one end. So I had to put 2 of them on there. And on the other end, I created this. So I put a row of pins on there. This is just a PC board that I then trimmed and made it smaller. And then I put a connector down the middle to plug the 50-pin connector on. But they're too close to fit across the gap on the board. So then I had to put another row of pins on each side of it to stab down on this board. So then I can break out all the pins. So I'm just going to plug this in. I think I got that right. And then what I did when I broke all these pins out, the green, I broke them off on this one breadboard. So I get this one breadboard pretty much just to break out this connector. This breadboard on the end, just break out the connector. So the green is for address lines, the blue is for data lines, and the white is for control bus. And then the red is for power, and then the black is for ground. So I'm going to turn this on. And it comes on fine. Still ringing like it should. And I wrote a program that I have on here onto the EEPROM. Now this is a 8K by 8 EEPROM, so it's actually 8 kilobytes of ROM. Actually, on the board itself, it only has 4K of RAM, so I've got a lot of ROM on there now compared to the RAM that's on the board. And then I also added on this another PIA on there, which is a peripheral interface device. So this is 6821, which is actually created to work with the 6809 or 6800 series, I should say. And what it has 2 output ports. It has port A and port B, and both ports have 8 bits. And you can have those 8 bits could either be input or output. So the red lines here, just for a demonstration, the red lines here go to port A, and it goes to the green LEDs, and the yellow wires here go to port B and go to the blue LEDs. And that's just to make sure that things are working right. And then I wrote a program, not this one, it's a different program I put in, and wrote it onto the ROM itself. And what this program does, it tells the processor to control the PIA. And it tells it to make all the pins output pins. So no input, they're all output pins. And then it's just going to increment a count from 0 all the way up to where they're all FF, and then go back down and go back up again. So it's going to continually count, increment one at a time. Excuse me. And the green LEDs, I had them set up, they're just going to rotate to the right. So they're going to continue to rotate to the right. So to get to this program, I first had to tell it where to go. So if you do a shift go, that means you want to go and run a program. So it wants to know what address your program's at. The program I wrote on here is actually at 6,000 hex. So I put 6000, and then once it's there, you push the plus sign to execute your program. And there you go. So right now, the processor is reading the commands on this EEPROM, and those commands are telling the processor to control this PIA device. You see, it's continually counting binary up to FF on the 8 bits on the right, and then 8 bits on the left. It's just going to rotate to the right. Now, this is actually, it goes through the commands on here, goes through and initialize both ports, and then it gets into a loop. And in that loop, it first rotates this one to the right, and then increments this one 1, and then goes in continuous loop, non-stop. So right now, it's just stuck. You see, there's no display on here. It's just stuck in a loop, a purpose loop. It just loops forever, and I don't have any way of interrupting that except for hit the reset button on the back. Hit reset button, and gets back to normal like it was before. And actually, I can actually access this manually or direct instead of doing it through the program I wrote. I can actually access it direct. And the way I do that, I first I'd go to the address. The base address is at A000. It shows 00. Now I want to change the data at that address. And the way this is set up, and this is the way the PIA is set up, if you set 00, those 8 bits, this is the A port. It's on my A port now. If you set 00, it'll set all those ports to read only. You set them FF, it shows them as output. Well, I want to make them outputs because we're controlling LEDs. So I make FF, so they're making them all output ports. And then I go to the next address, and this is the address you go to enable that and make it work. And the way you do that, type in a 04, and that 4-bit enables those registers. So now it shows it reset it back to 00, but now any I type in here will be displayed on those green LEDs. Like if I type in FF, all of them are lit, or 00, none of them are lit. Or if I want to do a 11, so it shows a 11 here, it's a 11 there. Or if I want 22, it shows a 22. Or an AA, shows an AA. So it shows a 1010, it's an A and an A. So now I'm manually controlling the PIA through this keypad instead of having it programmatically controlled by the program written on the ROM chip that I created. I'm not sure what my next step is on this. I've been kind of, once I breadboard all this, I kind of thought about actually breadboarding a whole PC from scratch onto breadboards. I do have 6809, a 6802, a 6800, an 8086, all kinds of different 8-bit processors laying around. So I could use one of them and do that. I just haven't thought too much about it. I might use a 6802 or a 6809 is where I'm pushing right now, is one of those. Anyway, I just wanted to show this off and see what you guys thought. And that's it. Thank you for watching.